Good afternoon, everyone. So today we will discuss the design of truss girder bridges. We will discuss part two now. In part one, we will discuss. We have already calculated the various forces in the members, that is the top chord member, bottom chord member, vertical member, and inclined members. So using that forces, we will design the various members. So these are the forces which have already calculated the last time. Okay. So this is my member. This is the upper chord member. So you will see that here the force is compressive in nature, no tensile force. And this is my bottom chord member. Here is a tension force. So generally in truss girder bridges, the top members are in compression and bottom chord members are in tension. And this is my vertical member. We have both the forces here, compression as well as tension. And this is my inclined member. Here this is the force, this is the compression, and this is the tension. So in case of vertical members, we found that the compressive force will be large as compared to the tensile force. But in case of inclined members, the tension force will be large as compared to the compressive force. So using these forces, we have to design the various members of the truss. So let us start the design of the top chord member. So what is the design force here? This is my design force. Okay. Now, first of all, I have to calculate what will be the depth of truss girder. So depth of truss girder, it is given in the problem, is we have already calculated, that is 6 meter, 6,000 millimeter. Now, depth of top chord member. We have to first calculate what is the depth of top chord member, which is generally taken as 1/10th of the depth of truss girder. So this is comes out to be 600 millimeter. Okay. So this is my depth total from here to here, that is your 600 millimeter. Now come to the width of top chord member. How much is this width which is required here? Okay. So this width is equal to depth of top chord, which is 600, plus twice the thickness of gusset plate. Now in this we have taken the generally taking the thickness of the gusset plate as 22 millimeters. So this is my gusset plate, this one. This is 22 millimeter gusset plate here and 22 millimeter here. So this distance from here to here, this is your 600 millimeter. 600 plus 22 here, 22 here, I will get the width of the top chord member. 600 plus 2 into 22, that is 644. From here to here, that is your 644. So my depth of the member is 600 and width is 644. Now we have to choose the section like this. Okay. Now these are the some criteria which are given in IS 1915 regarding the design of various members. So here, if you are designing the chord member, that is the top chord or the bottom chord, you have to take the effective length of the member as 0.85 times the distance between centers of the intersection with the web members. Okay, 0.85 times the distance between the centers of the intersection with the web members for calculating the effective length of the chord member. If you are calculating the effective length of the web members, that is vertical member of the inclined member, then you have to use this one, 0.7 times the distance between centers of intersection with the main chord. Okay, that is the top chord and the bottom chords. That you have to take the distance between the top chord member and the bottom chord member, which is in our case it is 6 meter. Okay, and here the distance between centers of intersection with the web members, we have provided the beams, okay, floor beams at a distance of 5 meters. So this is 0.85 times the 5 meter. Now we have designed the trusses with the help of working stress method. Okay, so these are my permissible stresses in axial compression for steels with various yield stresses. So this is my yield stress values here, and this is my slenderness ratio here. Okay, now we are given in the problem, we have to use this steel Fe 260, not 250, it is 260. So corresponding to this yield stress, I have to calculate the permissible stresses in axial compression here, corresponding to the slenderness ratios. Now this is my section for the top chord member. So for this member, the approximate radii of gyration are Rx is equal to 0.39 times H. Okay, so H is given as 600. We have already calculated in the previous test. So this is my Rx. Ry is 0.5 times H. It is equal to 354. Now these Rx and Ry, these are already well established section for truss girder bridges, and we have already known the radius of gyration of such type of section. So that's why I took it directly from the previous literature. Okay. So R minimum here is 234. Next, length of the member is 5 meter, that is 5000 millimeter. So effective length as per IS 1915, it is for chord member, because this is my chord, it is 0.85 times of 5000. So this is 4250 millimeter effective length. Next, I have to calculate the slenderness ratio, L by R. So this is my L and R is 234. So this is 18.16. Now corresponding to this L by R, I have to choose the permissible stress in axial compression. Okay. So this is sigma AC, that is the allowable stress in axial compression from the table which I just shown you in the previous slide. It is 154.34 MPa. Now I have to calculate how much area is required. Okay, so this is my force in the top chord member. Okay, and this is my stress. So I divided this force by the stress. So I required this much of area for the top chord. Now for this, I have to provide area which is bigger than this area. Okay. Now first of all, I have to provide a plate here at the top of this. I can say that the top chord member here. I have to provide this plate. So I have to calculate the width of top cover plate of the section between center to center of the rivet line. Now suppose that this is my rivet line. Rivets are here as well as here. So what will be the distance from here to here? So this is how much? This is 644 from here to here. Now this plate is 12 millimeter here and 12 here. So 12 into 2 plus this is my CXX. Okay, here the rivets are inserted here. So this distance is CXX. It is given in the steel table. So CXX is here. Similarly, CXX here. Okay. So CXX into 2. Okay. So this 644. This comes out to 24. CXX is given in the steel table as 26.4 into 2. So this is required 720.8. So the distance from central line of this rivet to the center line of this rivet is 720.8. Now, as per the code, maximum width of the plate element between line of rivets should not be more than 50 T. The code says that the distance between this rivet and this rivet should not be more than 50 T. Okay, where T is the thickness of the curve plate. Now here I choose the curve plate as 16 millimeter. So B by T should not be more than 50. B is 720.8 calculated here. T is the thickness of the plate. So this comes out to be 45, which is less than 50. This means that it is okay. Now total width of the top cover plate will be equal to how much? 720.8 from here to here. Okay. Now I have to add this much distance, which is called your edge distance here. This edge distance, it is given as EXS is equal to 53.6. So I have to add 53.6 twice, one here and one here. So this is 828 millimeter. So the distance from this, from the edge of this angle to the edge of this angle is 828. Now I have to increase it, say 850 millimeter. Okay, so this is the total distance from here to here, which is nothing but your 850. Now here I increase the plate width here so that the rainwater may not come inside the section here. Okay, this is just to safeguard the rainwater entering the section, because otherwise it will corrode this section. Okay. Now come to the area provided. How much area is provided here? So top plate is how much? 850 is this length and thickness is 16. So this is my area for the top plate. Two web plates. This is my one web plate here, one web plate here. This is how much? 2 into 600 into 12. This thickness is 12 and the depth here is 600. Okay, so this is my area. Then 4 angle, 1, 2, 3, 4. Okay, 4 ISA 80, 50, 60. So this is the area of one angle. So 4 angles is this much area. Okay. So total area comes out to be this much. Okay. Now I have to calculate the center of gravity of the section from the top fiber. Center of gravity of this section from this top fiber. I have to calculate first Ixx, then Iyy, and see which one is maximum. Okay. Then we calculate L by R ratio. Okay. So this is my Y bar from this top fiber. So this is the formula. Just I put everything here. A1 is first I took the plate here. So 850 into 16 into half of this 16 is 8. So this is my 8. So this is my A1 here and this is my Y1. Okay. Plus now one angle here, one angle here. I took two angles here. Okay. So 2 into this is the area of one angle. Okay. So this is my A2 into Y1. Y1 is the distance here. You will see that this is CYY. How much it is? 11.6. So 11.6 here plus 16 here. So that will be the distance from the top fiber. Plus two angles, that is your bottom angle, this angle and this angle, into Y1. This total depth is 600 from here to here. Okay. So in this 600 minus, this is again CYY from here. Okay. This distance. Okay. 11.6. So you will get the distance from here to here. Okay. Then I have to add 16 here to get the distance from the top fiber. So this is the plus 16 here. Okay. Now come to these plates. One plate here and the one plate here. 12 thickness. So 2 into 600 into 12. Okay. Into Y1. Y1 is how much? This is 600 meter depth. So half is 300. So 300 here plus 16 for this top plate. So this is come from the top fiber divided by A1 plus A2 plus and so on. Okay. So I got the final answer as 180.8 millimeter. So the distance of Y bar from the top fiber is 180.8, and from bottom fiber you have to subtract this value from 600. You will get this value here, 435.2. Okay. Now come next calculate. I have calculated Ixx, moment of inertia about Ixx. So how much is this? This one here. Now first I took these two plates, this plate and this plate. Okay. So two plates are here, 1 by 12. B is this one. 12 means 1.2. I convert it into centimeter. And then finally I multiply it by 10 here to convert again into millimeter. So in this way calculations are easy. So 1.2 is this one. D cube is how much? 600 millimeter. So that is 60 cube. 1 by 12 BD cube plus twice into area, because this section is now unsymmetrical because of this plate here. So that's why I have to calculate, I have to use the parallel axis theorem. So twice into area, 60 into 1.2 into h bar square. So h bar is how much? This half is 30 here. Okay, 30 minus, so this 1 cg is 30. The other distance is this one, how much? 180.8, that is 18.08. So 30 minus 18.08 whole square. Okay. So this is moment of inertia about CG from here to here, 1 by 12 BD. And this is by parallel axis theorem, that is your area times h bar whole square. Okay. Plus 1 by 12 BD cube for this top plate is neglected because the depth of the plate is only 1.6 centimeter. When you take it cube, it is small, so it is neglected. Only I took the area times h bar square. So area is how much? 85 into 1.6 into h bar is how much? This distance is 18.08 minus half of this. How much it is? 0.8 whole square. Okay. Plus 4 into Ixx. This is the area I of the angle about x-axis. 4 angles, 1, 2, 3, 4. 4 into Ixx plus area times. Now here, two angles are above this axis, two angles are below this axis. So I took the area times h by square separately. So for this two angle, that is the top angle, twice into area into h bar square. H bar square is how much? This is 18.08. Okay, minus This is how much? Cyy here. Center of gravity of this angle. How much? 1.16 plus 1.6 here because of this top plate. So 1.16 plus 1.6 whole square plus 2 into area for these two angles, bottom angle, 2 into area into h bar square. How much? This CG, this neutral axis is 435.2 minus this Cyy from here. How much it is? Again 1.16. Here it is 1.16 from here. So similarly from here also into 10 power 4. So this comes out to be, when you calculate all these things, this comes out to be I-axis in this case. Next, I have to calculate Iy, moment of inertia about this y-axis. Okay. So again, 1 by 12. This is my B is for top plate is how much it is? 1.6, and D is 850 in this case. So it is 85 kg. Okay. Plus moment of inertia 2 mm plates is neglected. This plate and this plate moment of inertia is neglected because depth is small. So dq is very, very small. So it is neglected. Plus twice into area. So I took the parallel axis theorem here for this plate and this plate. So twice into area into h bar square is how much? This is 644. So 644 half is how much? 32.2. Okay. Plus CG here. This distance is 12. So CG is 0.6. So 32.6 plus 0.6 whole square. Clear? Plus this is the moment of inertia of the angle about y axis. Okay. So this comes out to be y is this much. So we'll see that moment of inertia about x-axis is less as compared to the moment of inertia about the y-axis. So this is my weaker axis. Okay. So I have to calculate L by R corresponding to this value. So R minimum is equal to how much? Under root I over. This is my I about x-axis. This is my area already calculated in the previous system. So this is your R minimum. Slenderness ratio is L by R. L is already calculated, effective length, then it is 0.85 times of 5 meter. Okay. And here it is R minimum. So this is 20.37. So from IS 800, I have to select the allowable stress in axial compression. If this comes out to 153. Okay. Then load, I have to check whether the load carrying capacity of the member is more than which is required or not. So this is my stress. Okay. Multiply by this is my area and convert into kilonewton. So this is my value. This is the load carrying capacity, which is more than the force in the member. Okay. So this means that our choosing section will be safe. Okay. So this is the design of the top chord. Next is before coming to the design of the bottom chord member and vertical inclined member, I have to use this table again, which is given IS 1915 steel code. This is factor K for fluctuating stresses. You know that when the stress is changing from tension to compression or compression to tension, we introduce the fatigue stresses, because in bridges, okay, in vertical members and in the inclined members, the force is changing from tension to compression and compression to tension. So that will introduce fatigue stresses. To account for this fatigue stresses, we have to reduce the value of the permissible stress in axial tension. Okay. So this table is used for that. So here, what it is given here, this is F minimum by F max. So F minimum means minimum stress, minimum force. F maximum, maximum force. Sometimes this minimum, both are tension. These were these values, both tension here, tension here. Sometimes this is tension, this is compression. Sometimes this is compression, this is tension. Okay, depending upon the type of the force. Okay, so we have these values here. One from 1.0 to 0.0, these are positive values, and this one are all negative values. Okay, now these are the number of cycles. You know that fatigue means the number of alternating cycles of tension and compression. So this fatigue cycles are 1 into 10 power 5, 6 into 10 power 5, and 20 into 10 power 5. Sometimes we took this value, sometimes we took this value. Okay. Now suppose that if the member is subjected to both tension and compression forces, then we have to choose this value, 20 into 10 power 5. More number of cycles. We have to design it for more number of cycles. Okay. Now suppose that if the member is subjected to only tension, but it is fluctuating between minimum and maximum, but both are tension values. So in that case, we took less number of cycles, that is into 6 into 10 power 5. And we will use only this one, this first cycle 1, 2, and 3. Why? Because this is required here K for steel members conforming to IS ETNA fabricated with or connected by rivets. So rivets or bolts. So these values are used when the connection between the truss members are with the help of rivets and bolts. These three columns are used when the connections are only with the help of welds. Okay, so in our case we don't use weld values, so that's why we do not use these values. Okay, and these last three columns are for high tensile steel. So we are using only 260, so which is this one. So that's why we will just concentrate on this value. Okay, now I will come to the design of bottom chord. So force in the member, this is already calculated in the force. We have already calculated this. Now to allow the effect of fatigue, the allowable working stress in tension, axial or bending is reduced as compared with the basic stresses. So my target is I have to reduce the permissible stresses in tension because to account for the effect of fatigue. Okay. So this is my minimum stress. If you just check the value of the various in which various forces are given, this is the minimum value in the bottom chord member and this is maximum value in the bottom chord. Both are tensile of the same sign. Okay, there is no tension and compression, but this is minimum, this is maximum. Okay, so first I have to calculate the ratio R, which is given by R, F minimum by F maximum. Okay, so this comes out to be 0.186. Now from the previous table which I just shown to you, K comes out to be 1.0 for 6 into 10 power 5 cycles. Just remember this R value 0.186. I will show you again the table here. Corresponding to the cycle 6 into 10 power 5, my R is 0.186. So R is 0.186. It is nearly equal to 2 here, 0.2, positive sign. Okay, and my number of cycles is 6 into 10 power 5. So this K value comes out to be how much? It is 1.0. Okay, so this value K is 1.0. Therefore, allowable stress in axial tension is how much? This is my formula for allowable stress in axial tension, 0.6 sigma y. So K factor is 1.6, sigma y is 260. So this is 156. Okay. So there is no reduction of stress, that is a permissible stress, because this K is 1.0. So net area required will be how much? This is my force and this is my stress. So this is the area which is required. Now this area is nearly equal to the top chord area. So that's why I choose the same section for the bottom chord member also, because the area is nearly same. So I choose this section. Okay, 600 depth as in the previous case, 600 width as in the previous case. Okay, but only change is that I use a different angles here, 200, 150 by 10. And here we have to provide the lacing here and here for the bottom chord member. Okay, so that any rain water may come inside, okay, from the sides, that will be passed from here. So we have provided lacing and not the solid plates. Okay, and we have provided here, this plate is your 8 mm, this plate is your 12 mm. Okay, now overall dimension of the section is kept same as that of the top chord member. So area provided to be how much? 2 web plates. How much? 600 into 12. So this is my 600 and this is 12. Okay, so this is my area. 2 additional plate with web. This is my additional plate. 8 here and 8 here. So 2 600 into 8. This is my area. 4 angles. Area of one angle, this one. Total is this one. So total area comes out to be this much. Now because it is a tension member, I have to detect the area of rivet holes which are required for connecting here, here, here and here. Okay. So let us assume 22 5 rivets, assuming that 20 rivets would be required for connecting the members and the lace. So 20 members are required for connecting. Now between these plates, we have to require some rivets here, we have to require some rivets here, we have to require some rivet here. In all, total we require 20 rivets. Now we have to deduct the reduction for these 20 rivets. So area of rivets hole will be how much? 4 into D into T. Suppose that I took one rivet here, one here, 2, 3 and 4. Okay, so 4. Now the diameter of the rivet hole will be 1.5 millimeter more than the diameter of the rivet, as you know from the BTech level. Okay, so this is 1.5 more is 23.5 into how much is this thickness here? 10. So this is my 10. This is the reduction over the area. Then 4 rivets are connected here. 1, 2, 3 and 4. So 4 into D, diameter of the hole, into thickness. How much is the thickness here? This is 10, this is 8, this is 12. So 10, 12 and 8. Okay. Then so 4 rivets are connected here, 4 here. How much used? 8 used. So remaining here 12. So 12 are connected in the plates here. So 12. So 6 on this side and 6 on this side. So total 12. 12 into D into 8 plus 12. So this is my 8. This is my 12. Okay. So total area is this one. This is the deduction for the rivet hole. So I have to provide the net area in tension member. So my total area is this one minus area of the rivet hole is this one. So this comes out to be this much, which is more than the required, which is calculated in the previous slide. Okay. So this is more than the previous area, that is the required area. So this means that our section is okay. Now come to the design of vertical member. In vertical member, the compressive force will be large and the tensile force will be less. Okay. Now the overall depth of the vertical member is kept equal to the inner width of the top chord member less twice the thickness of the cassette plate. Now consider it this how much is the depth of required for the vertical member. Remember the top chord member having the depth as 644. Okay, having width as 644. Now in this 644, 600 is the gap between the two members and 22 millimeter gusset plate on the two sides. Okay, so I have to choose this depth as of the member as 644 minus just remove the gusset plates, so that this member, that is the vertical member, is fit directly into the top chord member. Okay, that's why I reduce it. So 644 minus 2 into 22, that is 600. Length between center and intersection for vertical member, the depth of truss girder is 6 meter. We have already calculated in the first step on the last lecture. Okay, so effective length will be how much? From the IS code, effective length is 0.7 times this length for the vertical and the inclined members. So this is my effective length. Now, assuming the allowable stress in axial compression for 260 MPa and slenderness ratio 70 as 115. Now, why I choose 70 here? Slenderness ratio for rolled steel beam, slenderness ratio is generally lies from 70 to 90. So I took a minimum value here, 70. Okay, this is on the safer side. So what I will do now, this is my vertical member. Okay, we have provided 4 angles, 1, 2, 3, 4. We have provided a lacing in between here. Okay, this is my lacing. Clear? Now, what is area required? This is my maximum force in the vertical member divided by permissible stress, which I have already calculated in the previous slide. So this is the area required. Clear? Now for this, I provide 4 angles. 1, 2, 3, 4. 4 SA, 125, 75, 8. Okay. So area provided is how much? You have to take this area from the steel table. So this is my total area. Okay. Now, because the compressive force in this vertical member is high as compared to the tensile force, so I design this member as a compression member and check it for tension also. So first, I will design this member as a compression member. That's why I calculate IXX and now IIYY. And then in the last, I have to check it as a tension member also. So this is your IXX, moment of inertia about XX axis. So how much it is? 4 into, now this is your symmetrical section about XX axis. So 4 into Ixx plus 4 into area into h bar square. So this is my axis here. So h bar is how much? This is my 600. So half is your 30 minus this is your Cy bar 1.68 whole square. So this is my Ixx. This comes out to be Ix is this much. Then I have to calculate Iyy. This is my yy axis. Okay. So this yy is equal to 4. This is my Iyy plus area times 4 into area times h bar का whole square. So h bar will be how much? This is Ex. You see that Ex is 4.15. This is CG of this angle. So this CG plus this half distance. So the distance between this and this is 10 millimeter. So half is how much? 5 millimeter means 0.5. And I convert into 10 by multiplying 10 here. Again convert it to millimeter. So this is your 4.15 plus 0.5. Okay. So this is my Iy. Clear? Now here you see that Iyy is less as compared to Ix. So I have to calculate the slenderness ratio corresponding to this one. So R minimum will be I over A. So this is my I and this is my area. Okay, this is my area provided. So this is how much? 61.31. Calculate the slenderness ratio L by R, which comes out to be 68.5. Okay, again from steel table, I have to calculate the permissible stress. So this is my permissible stress. Then in the last, I have to check the load carrying capacity. This is my stress. This is my area provided, converted to kilonewton. So this is my force, which is more than the force in the member. That means it is safe. So I designed this member as a compression member. Why? Because the compressive force is large in this member. Now I have to check it to check the member for tension also, because some tensile force is also there. So this is my F minimum. Okay, this is my F maximum. This is your compressive force. This is my tensile force. Okay, so I have to calculate R, F minimum by F maximum, because there is a fatigue because of this change of stress from tension to compression, tension to compression. Okay, so this is my R is how much? Minus 0.66. So I have to now here I took 20 into 10 power 5 cycles. Previously I took 6 into 10 power 5 cycles. When these forces are both of the same sign, suppose that these two are of tensile forces, okay, then I took 6 into 10 power cycle, less number of cycles. But when there is a tension and compression, okay, so alternating stress is there, then I have to go for more number of cycles. So this value K comes out to be from the table 0.63. And mind it, you have to take R from this negative sign here, okay. So therefore, allowable stress in tension along the effect of fatigue will be how much? This is my K factor, this is 0.6 and Fy is 260. So this is 98.28 MPa. Okay. So net area required will be how much? Will be equal to, this is my stress, that is your tensile stress, divided by, tensile force divided by the stress. So this is my net area which is required. Okay. Now gross area provided is more as compared to this one. So this means that the design is safe. Now I have to just apply the area for the rivet hole also, because it is a tension member now. I have to check it as a tension member. So I have to detect the 4 holes. 1, 2, 3, 1 here, 2 here, 3 here, and 4 here. Okay. So 4 into D, and the thickness of this member is your 8 millimeter. So this is my deduction for the rivet hole. So net area provided how much? This minus this. So this is 5400, which is more than the required. Hence, it is your safe value. Clear? Now, last is your design of diagonal member. In diagonal member, tensile force is maximum, compressive force is minimum. So again, I have to calculate R value. Now, because the tensile force is maximum, so I just designed it as a tension member. I did not design it as a compression member. Okay, in the previous case, the compressive force will be large. That's why I designed that vertical member as a compression member and then check as a tension member. Here the tensile force is maximum, so I just design it as a tension member. So this is my compressive force. R is equal to F minimum by F maximum. This is my minimum. This is my maximum here. So this comes out to be the same value, that is R minus sign. Okay, so again K values remain the same. So again allowable stress in axial tension along the effect of fatigue will be how much? Same value. So again same stress. Net area required is how much? This is my force now because I design is a tension member in divided by stress. So this is my area. Now because it is a tension member, so I have to do the some deduction for the rivet holes. So these are the members angles which I provided for the diagonal member. Okay, slightly change section as in the previous case. Here in the previous case it is 8 millimeter. Here it is 12 millimeter. So for ISA 125 95 12. So gross area provided will be how much? 4 into area of one angle. So this is the total area. This is the deduction for rivet hole. 4 into D into thickness is 12. Okay. So this is my deduction. This minus this, I will get this. So this is more than the area required, which is this one. Hence it is safe. Okay. So this is the last step. That is how the members are connected in case of trusses. So you'll see that this is my bottom chord member. Okay. Now there is a certain width perpendicular to this slide. Okay, perpendicular to this slide. So this is your width of the. This is my depth and width is perpendicular to the slide. So this is my bottom chord. Okay. Now this is my inclined member here. This is my inclined member here. So we have provided inclined members angle section. Okay. So one angle here, one angle here. So these are the connection of these angles. Connection of these angles with this gusset plate. Just remember, recall that in the design of the bottom chord member, we have provided a gusset plate. So that gusset plate is extending from the member so that we can connect the inclined member as well as the vertical member with the help of this gusset plate to the bottom member as well as at the top. Okay. So similarly, this is a connection here, and this is my vertical member. Again, we have provided angles here. Okay. So these are the connection of the angle 1, 2, 3, 4 rivets here, 4 rivets here. Okay. So this is perpendicular to the this slide, the vertical member. Okay. Again, this is perpendicular section perpendicular to this slide. Okay. So in this way, we have provided the connection, various connection between the members. So this is all about the design of complete design of the truss girder bridges. We have designed the 4 members, that is the top chord member, bottom chord member, vertical member, and the inclined member. Thank you so much.